In this chapter, we are going to explore advanced token security mechanisms. After successfully completing authentication and authorization, the client obtains an OAuth 2 access token from the authorization server. This token is used to send requests to the resource server. This process is common across all OAuth 2 flows. For example, in the authorization code flow, the client receives an access token from the authorization server, which it can use as proof to access resources on the resource server. Similarly, in the client credentials flow, the client receives an access token directly and can immediately use it to request resources from the resource server. But what happens if the access token is intercepted or ends up in the wrong hands? An attacker could then use the access token to impersonate the client and send requests to the resource server. The resource server would validate the token, confirm it's valid, and send back the requested resources, effectively enabling the attacker. This scenario is technically correct because the token is valid, but it is definitely not what we want. And this brings us to the critical question: how can we ensure that the access token is used only by the intended client? This is exactly where advanced access token security mechanisms comes into play. In OAuth, there are two mechanisms that address this issue: X500 Mutual TLS, MTLS, and Demonstration of Proof of Possession DPoP. Both mechanisms are part of the FAPI2 standards, which aim to enhance security and interoperability in high-risk environments such as financial services. We have already discussed X509 MTLS in previous lessons as a client authentication method. Now we will explore how it functions as an advanced token security mechanism. In simple terms, X509 MTLS ensures secure access token binding by leveraging the TLS layer. During the TLS handshake, the client presents its X509 certificate, and the access token is issued with a CNF confirmation claim that includes a hash of this certificate. This binding ensures that the token can only be used with the same certificate that was presented during the handshake. When the token is presented to the resource server, the server validates the certificate against the CNF claim to confirm that the token is being used by its rightful owner. In contrast, DPoP operates at the application layer. To start, the client generates a key pair, a private key and a public key. The access token includes a CNF claim containing the hash of the client's public key. For each API call, the client must provide a DPoP proof, a signed JWE generated using the private key, corresponding to the public key in the CNF claim. The resource server validates the DPoP proof and the CNF claim to ensure that the token is bound to the client and cannot be misused. This approach doesn't rely on the transport layer, but instead uses cryptographic proofs at the application layer. Now that we have introduced the two mechanisms, let's dive deeper into the X509 MTLS approach.